Okay, we should be recording now. Okay.
Okay. Hi, my name is Mike Miller. I'm an independent software developer, independent AI researcher. And today we are going to discuss coordination. So there's a series on YouTube at sign cognitive architectures. And the series is about building minds with design patterns. And essentially, today we will talk about one aspect of building minds, which is integrating inferences in a cognitive system. In the first, this is the second of a three-part talk. In the first talk, I talked about creating an artificial mind, the genesis of an artificial mind. Started that with a little story. And we talked about observation, what it takes to perceive for an artificial mind to be embodied. And this talk, and you can find those talks on YouTube. The Genesis talk in particular is available. It's been up for some time. And we're going to talk about coordination. So this is the second in the three-part series. And eventually we will put a talk on YouTube for coordination. And then the last part is development, the development of an artificial mind from infancy through adolescence. So coordination. This is a template for an AGI system. And in this template, we can see a mind in the square, an artificial mind, interacting with a device that's situated in a world, whether the world is artificial or is virtual or real. The device could be a robot, it could be a smartphone, it could be any kind of device. And the device sends observations or observables to the mind, and the mind has different mechanisms, different components that intercept the observables and place the observables into memory. Once the observables are in memory, we have coordination mechanisms which add inferences to the memory. These inferences are called coordinations. And then acting upon the inferences and the observables, we have reflection components which modify the behavior of the overall system. And then finally, we have consolidation components. And the consolidation components will make sure that the memory doesn't exceed a certain utilization or a certain capacity. So consolidation components keeps the memory compressed through various processes, forgetting, automaticity, and other compression strategies. So today we're going to focus on coordination. And coordination is basically adding inferences to the memory in addition to the observables. We have several coordination components. These are groups of mechanisms. We have what are called activators, propagators, associators, chunkers, solvers, and reasoners. So the coordination pattern creates inferences to augment sensory observations. This covers a range of processes, including proposition activation, belief propagation, proposition association, concept induction, action synthesis, and operation synthesis. The inferences created in this process are called coordinations. In Jean Piaget's vernacular, there are observables, which are sensations, and coordinations, which are inferences. Assimilation and accommodation are Piaget's fundamental processes. Assimilation is the formation of new schemes that incorporate observables and coordinations via association, reasoning, and problem solving. And since they form new schemes, the assimilation mechanisms include the associators, the solvers, and the reasoners. Accommodation is the modification of existing schemes by association, chunking, and negation. Since they modify existing schemes or belief parameters, the accommodation mechanisms include the activators, the propagators, and the chunkers. The coordination pattern involves all of these mechanisms interacting with a shared memory called the totality. Don't Think of an Elephant by George Lakoff. Activating.
Why not?
Activating. The activator mechanisms are responsible for transferring activation among propositions contained in the knowledge base of an artificial mind. In biological systems, certain cells called excitatory cells or telegraph cells have the capacity to generate and transfer electrical impulses among themselves. This is known as spiking or firing. In artificial neural networks, this phenomenon is mimicked by the assignment of weights to nodes called units. In general, artificial neural networks have activation functions that update synaptic connections among nodes across layers in the network. When a connection exceeds a predesignated threshold of activation, the nodes with connections above the threshold are considered activated, while those below the threshold are considered inactive. Activated nodes on a particular level of the network contribute to the activation of nodes in subsequent layers of the network. And in semantic networks, a process called spreading activation makes certain nodes in the network relevant when contextual cue concepts are presented to the network in order to imitate the priming effect found in cognitive psychology. That is, when people recall information quickly once a related cueing concept is presented to them. In all cases, each cell or node is presented with a stimulus, and other cells or nodes are affected in certain biological or synthetic ways. Activation is said to transfer from one cell or unit to another. The notion of activation in the totality is quite similar. For propositions contained in the knowledge base of an artificial mind, activation time is transferred among propositions based on several factors. So we'll now talk about the totality. The totality is a Euclidean coordinate space. It has tiers, it has columns, it has rows. It also has realities and viewpoints and activations. We'll get into these in a little bit more. The memory unit of the totality is called a scheme. A scheme has several parts. It has a reifier, which identifies the scheme. It has a relation. It has arguments. It has reference. The reifier is the identifier for the scheme. The relation is a reifier for the relationship. The arguments is a list of input reifiers to the relation, and the reference are a list of output reifiers of the relation. It also has other supplemental structures, one for each of the arguments and one for each of the reference. These structures are called brushes, and they help. They are not schemes, they are separate structures. They're akin to join tables or associative entities in database vernacular. A reifier can also be represented as a message. A scheme can also be represented as a message with the various parameters: reifier, relation, arguments, and reference. What holds the schemes in place is glue or glial cells. And basically the glue is also a brush. It's also a join. And essentially it has coordinates, and it has X, Y, and Z variables. And the glue connects to the scheme via the reifier. So the reifier is the connection between the glue and the scheme. And so basically there's an isolation between the coordinates and the data that's being represented, or the proposition that's being represented. Typically the reifiers are on a higher tier. The referents are on a higher tier than the reifier, and the arguments are typically on a lower tier. So the schemes, as they occur, get placed into the totality.
This might not be the right time to ask, but maybe there's.
Essentially, the glue cements the reifiers into the totality. So every scheme will have a particular location in the totality. Schemes also have lexemes, and they have usages. A scheme may be associated with a particular piece of text, a label, and so the label will have its own place, as well as the usage or reference count of the scheme. A schema is a subsystem of schemes. And typically, for a schema, each of the arguments and each of the reference get their own scheme. We have various mechanisms that manipulate schemes directly. One is the assimilator, the lexer, and the accommodator. And they have different messages that they respond to. The assimilator makes schemes. You give it a particular totality, relation, arguments, and reference, and it'll create a scheme. It can also make brushes, the joins, by giving the slots and values for the join. The lexer allows you to label schemes. If you give it a totality and label, it will find the scheme via the label, and if it doesn't find the scheme, it'll create one. And it can return the label for a particular reifier. And the accommodator copies schemes. So it copies schemes with possible modifications. You pass in a reifier, and it will potentially substitute the relation, add arguments, add reference, remove reference, or substitute arguments and substitute reference. There are different regions of the totality. There's the perceptual region. So percepts or observables come in at the bottom, and they generally have no arguments or reference. And so they sit at the bottom of the totality. Then the percepts generate features through detectors. So the detectors will take a percept and identify what features of the percept exist. So we have another layer above, which is the feature layer. Then entities, which are assemblies of cross-modal percepts. We have the conceptual level. We have the level of events. We have the level of episodes, which are groupings of events. We have a behavioral level for actions and planning. And then we have an operational level for reasoning and inference. We have an individual mind and the mind is situated in a reality. But we also have, for this artificial mind, we can have the observed reality, we can have the desired reality, we can have what we expect or an expected reality. We can do some problem solving in a possible reality. We can look at what has been attained, what has been confirmed, what has been imagined, and what has been recalled. So we have different realities or different ways of dealing with this totality. And the schemes can be activated independently depending upon what you're doing. So the observed reality is for empirical sensory experience, the current model. You have the desired reality, what is desired in the future, what is expected in the future, which may differ from what you want. You know, possible reality is for hypothetical reasoning and self-directed problem solving, attained, confirmed, imagined, and recalled. Finally, we have viewpoints. Sri Nisargadatta Maharaj said, "I am that." By that, he meant that we are pure in awareness. The only true statement we can make about ourselves is that we are. Viewpoints. A viewpoint is a ray of fire which indicates a context for activation and reasoning. The first viewpoint is awareness. Other viewpoints are created and adopted over time. So we have in our totality, it starts out empty, and we have general awareness. We create a distinction in the totality, which is in the general awareness viewpoint. And then we can create more distinctions. And this is typically how Piaget views that children develop. Over time, we identify ourselves as something in the world, as an object in the world, and we become self-centered. And then we also identify other people in the world and other perspectives. And this leads into, at the age of 2 or 3 years old, what we called the ability to see things from other people's perspective. And so we may be able to see things from, other people's perspective. It's called theory of mind. And then eventually we get into a positive view of ourselves, which we promote to the world, which is our Jungian ego. And over time, if we're lucky and if we're astute enough, we may even find the negative aspects of ourselves, which Jung calls the shadow. But these are all different viewpoints that we can take when we look at things, when we think about the world. So initially, we are just awareness. We develop a viewpoint of self. We can see things from other people's viewpoints. We eventually develop a positive outlook of ourselves. This is our view from consciousness, preferences, and responsibility. Then eventually, if we're lucky, we are able to see the negative aspects of ourselves, which we call the shadow. And this is our view from ignorance, aversions, and freedom. Finally, in this particular artificial mind system, we talk about time slices. And we take a year and divide it into a billion parts, a billion units. These are nanoyears, and we call these units moments. A moment is a 16-digit number representing a nanoyear. It's approximately 3/100ths of a second, a little more than 3/100ths of a second. And some examples of this unit are the following. A moment, we have an underlying language, and the underlying languages can create these units called moments. Finally, we're talking about activation and activating, and we talk about the spread of activation within the reality. So Activation is spread within a reality. It can flow in three ways. It can be dispersed upward from observables to coordinations. It can be dispersed downward from desired coordinations to observables, or it can be radially cascaded in all directions. When a scheme fires, it spreads activation within the totality. To do so, a scheme first coalesces the activation from its arguments to its reifier, and then it disperses the activation to its reference according to one of several flows. And this approach is based on what typically occurs in the biological brains. Coalescing or merging activation involves determining the activation time and activation signals of a reifier based on the arguments. And each scheme or neural proposition synapse has two interesting attributes, the activation time and the activation signal. There are 8 ways to merge the activation that we've defined. And these ways are 1, allowed, pass-through, not, and, sequence, or, nor, and vote. So 1, pass-through, not, and, sequence, or, nor, and vote. The merge type of the scheme's relations determines how to coalesce the activation. For the merge type 1, only one activation is permitted among all the arguments. Pass-through means that if an argument is activated, the reifier is activated. Not is the complement of the activation. And is an all or nothing activation. All the arguments have to be activated, or none of the, in order to activate the reifier. Sequence is a sequential activation. So if you have a list of arguments, the arguments have to be activated one at a time in sequence. Or is any activation will suffice, nor is no activations are allowed. And vote means that if you have a number of arguments, there has to be a majority of arguments active in order to activate. And different relations, we'll get to the relations pretty soon, have a merge type associated with it. So for example, categories have an or merge type, series have a sequential merge type, and unison has an and merge type. How are we doing on time?
Fine.
What time is it?
It's just
Okay, great. To disperse activation means to trigger updates by potentiating related schemes. Often these updates are based on a directional flow within a specific viewpoint or reality. And the observed reality disperses activation upwards from observables to coordinations, and from observed arguments to scheme reifiers, then laterally from arguments to reference within a scheme. In contrast, the desired reality spreads activation downward from desired objectives down to associated observables. The recalled reality cascades and attenuates activation radially within a viewpoint, so that when you recall something, it's not flowing the activation up or flowing the activation down. It's just saying, okay, what is associated with this? Let me spread out this activation from one idea or concept to related concepts, regardless of direction. So this is an activation structure. The activation structure has a particular viewpoint. Remember, we talked about general awareness. We start off with general awareness and then may take the self viewpoint or other viewpoints in the future. It has a particular scheme, a particular reality. Most often we deal with the observed reality. So we'll have the awareness viewpoint in the observed reality. Then it goes through and has a number of other parameters. But the viewpoint, reifier, and reality are what identify the particular context for activation. Enabled sense and impeded sense So if a reifier can be enabled at a particular time, or it can be impeded at a particular time, or inhibited. It can, if you enable it and then later impede it, we keep track of when it was enabled until, or when it was impeded until, vice versa. The pulses is the count of the activations, the count of the number of times a particular reifier was activated. So if 3 arguments activated this particular reifier, then we keep track of that. The merge type of the reifier is important, so we know which way, what will determine whether or not the reifier gets activated based on its arguments. And then we have the particular activation and the antipode of this activation. So if a reifier has a logical opposite, we want to be able to locate that logical opposite and quickly activate that or deactivate that as necessary. We have, regarding activation, we have a registry for the whole entire system, and some of the key values related to activation are the activation window, which tells you how long a particular scheme is considered active, a forgetting window, after which point we can start deleting schemes or cleaning them up. And then we have potentiation values. So potentiation is a time frame for associating, making new associations. And we have immediate, short-term, mid-term, long-term, and extended potentiation. And different kinds of associations are formed during those different intervals. So the activation window is typically 3 seconds. Immediate potentiation is typically about 1 second, and so forth. We have a lot of different activation mechanisms. There are 2 schools of thought in developing intelligent systems, in particular AGI systems. One school is the uniformity-based school, the uniformity-based architectures, and another school is the diversity-based architectures. Uniformity-first architectures try to emphasize a minimum number of algorithms and a minimum number of mechanisms or components. And, can look at the neural network field as one paradigm that champions uniformity-based approaches. And then the opposite camp says that there should be more than one or many different modules, components, mechanisms that will achieve intelligence. And so in the second school, we have different mechanisms that do very specialized tasks. So here we have different mechanisms. We can talk about the individual mechanisms. The activator is a mechanism. The job of the activator is to enable or impede individual schemes upon request. It gets messages such as the following: enable a list of reifiers at a particular moment, in a particular viewpoint, in a particular reality, or impede, these reifiers at this moment in this viewpoint and reality. And so the job of the activator is to enable or impede individual schemes upon request. If we have the activation structure and we get a message to enable reifier 8943 at a particular moment, if no reality of viewpoint is specified in the request, as such, there was this was all we got, it puts in defaults. So the default viewpoint is awareness and the default reality is observed. It will add that entry and then it will, likewise, if additional activate requests come in for the same rate of fire, the number of pulses is enabled until they're updated. So it will enable those. If we get a request to inhibit the rate of fire, then the pulses is reset to -1, and enabled and impeded fields are updated appropriately. And additional inhibition requests will update pulses and impeded fields appropriately. So if we get additional impede requests, the pulses and impeded times will be updated. The job of the Chronos is to expire activations by resetting the pulses field to 0. So if no other signals or requests are received for 8943 ray of fire, then eventually it will expire and the pulses will be reset to 0 by the Chronos mechanism. So for example, time has passed, was passed over 3 seconds, and we have so far it's been impeded 4 times. It gets reset to 0. So we have this Chronos mechanism just in the background, resetting the number of pulses. All the other information, all the other activation information is needed to be tracked, so it's kept. The observer, the job of the observer is to spread activation across tiers in a bottom-up fashion, from arguments to schemes and from schemes to reference in the observed reality. So we're propagating what we observe upward in the totality. The anticipator, the job of the anticipator is to spread activation across tiers in a top-down manner from reference to schemes and arguments in the expected reality. So if we are expecting or we anticipate something to happen, we're spreading that down from a top-down fashion, and we are looking eventually to see observables that confirm our expectations. The reminder, the job of the reminder is to spread activation in a radial manner across tiers, columns, rows in the recalled reality. So if we are thinking of something that we are recalling or remembering, we want to spread activation out to all the other associations that we have. You know, if we had a dog named Fido, right, we might think of Fido and then start remembering times when Fido chewed up our sneaker, or times when Fido went on the carpet, or times when we ran in the park with Fido, and so forth. So all of those memories start coming back to us, and they're because of their associations in all different directions. The dreamer, the job of the dreamer is to spread activation across tiers in a bottom-up fashion, from arguments to schemes and from schemes to reference in the imagined reality. So once we start, so people have two networks of switches going on in their brains. They have what we call the task positive network, which deals with your current attention. If you're doing something, you're engaged in it fully, and you need to handle different problems or issues going on, then your task positive network is working and your consciousness is actively engaged. But people also have something called the default mode network. And the default mode network is your daydreaming network. And so when you're in a mode that there aren't any surprises in your environment and you're pretty much handling the task at hand without thinking of it, you're in automatic mode, then your default mode network kicks in and you're able to daydream freely. This happens when you're doing the dishes or when you're driving a car or something like that. You're pretty much, there are no surprises going on. And so your task positive network switches over to the default mode network. And so the dreamer handles the activation that's going on in your imagined reality. So it spreads activation in the imagined reality. Propagating. While activators modify the activation of schemes, propagators modify the statistical belief parameters such as certainty, desirability, likelihood, reliability, and so forth for each of the schemes. This allows agents utilizing the proposition to leverage quantitative statistics about each proposition of interest to make informed decisions. Belief propagation, therefore, is the means by which statistical information about relevant propositions is updated. This is a continual process since propositions are continually created, modified, and forgotten. So in propagation, we have beliefs, and this is just a generic belief structure. And not all schemes will have beliefs associated with them, just like not all schemes will have labels associated with them. But for the beliefs of interest, we have the viewpoint and the reality and the reifier, which localize a particular belief, because you may have different beliefs about a subject, or different other people may have, beliefs about something, and you might hold the opinion that somebody else has about a particular topic. We have the valence and arousal, and basically emotion in the cognitive system is based on a simple notion of valence, the measure of good or bad, positive or negative feeling, and arousal, a measure of excitement or indifference. And this emotion can be ascribed to the sentiment of the artificial mind itself, as well as it can be ascribed to individual propositions via the belief parameters. So typically, this is a small scale from -1 to 1, whether or not you're apathetic or excited about, whether or not the system is apathetic or excited, and whether or not the system is feeling good or feeling bad. And this belief, emotional belief, can be ascribed to individual schemes. There's certainty and coherence. So your certainty about the particular scheme, or your coherence, how well does the scheme fit in with others? And then the likelihood that this scheme will be activated in the future, and the actions likeliest to make that happen. And then basically the identifier of this belief and the identifier of its logical opposite. You have actions, and the important beliefs about actions is the number of attempts the action has had and the number of successful attempts it's had. So you can just divide, you can find the reliability just by simply dividing the number of successes over the number of attempts. Needs, system has needs as explained in the first video, and the urge is the delta between the target value of the need and the actual value of the need. So a need for a robot might be electricity and Wi-Fi signal strength, and ideally the need would be 0. The delta should be 0 because it's fully charged, but as it gets used, the delta can change. Mechanisms that are involved in belief propagation. The gluer, when it detects a new scheme in the totality, it creates glue for it, and that glue will position the scheme into the totality. The arranger, this mechanism continually rearranges the matrix by updating glue coordinates in order to drift scheme arguments towards scheme reifiers on the XY plane. So you have arguments and reifiers moving closer together. Maintain sufficient distance between schemes. Keep reference above their scheme reifiers and keep scheme reifiers above their arguments on the Z plane. And then settle schemes having no arguments to the bottom of the totality. So as schemes are added, the arranger continually moves things around, shuffles things around to make things easier. The arouser. Arousal is based on the urgency of an objective. A scheme becomes aroused if it becomes an objective or desideratum. Desideratum is an objective for a logical proposition, or if it is activated in the desired reality. For urgent schemes, the mechanism creates a belief, and if the scheme lacks one, and updates the arousal value. If the dyad exists, it also adds a negative arousal to its dyad. The effector, the desirability, is based on the salience or the importance of the objective. Whenever the salience of an objective or a desideratum is recalculated, the valence of the scheme is also recalculated. And this mechanism creates a belief if the scheme lacks one and adjusts the desirability value of the belief and sets the negative for the desirability of its dyad. Coherence basically says how well a proposition fits in with other existing propositions. We'll pass on this for now. So the coherence value is used by the amniator agent to the forgetting agent to determine whether or not propositions can be forgotten. Non-coherent propositions will be forgotten before more coherent proposition. If a proposition or a scheme ties in with your beliefs, you're going to hold on to that a lot longer than if a proposition doesn't tie into your beliefs. For an objective, the likelihood of success is based on the applicability and reliability of the actions relevant to the objective and is measured on a scale of unlikely to certain. The estimator mechanisms finds the most relevant and applicable actions for an objective and computes a simple likelihood score based on the reliability. To live is to suffer, to survive is to find some meaning in the suffering. Friedrich Nietzsche. Associating, finding meaning. For the purposes of activation, schemas are circuits that control activation flow. The associated mechanisms make these circuits. So we're building a brain one circuit at a time, one neuron at a time, essentially. Observables such as percepts and features form the base of the totality. Image schemas reflect spatial relationships among the observables. Simple relationships between two schemes are called horizontal relationships, and vertical relationships reflect groupings of multiple schemes. Gate relationships control the flow of activation from arguments to reifiers. And structures reflect complex associations. So we're building up using all of these different circuits, we're going to build up our knowledge representation, our ontology. There are also several derivative circuits. So observables. So we have percepts, features, propriocepts, which are results of actions taken, and interocepts, which are urges that emanate from the device. You know, think of if we have a robot, the robot is going to have a power demand or power need, and that power need is going to fluctuate over time depending upon when it's charged and when it's not. Most likely the power will drain, and so we get an urge from the robot for power. The urge increases over time as the delta from the desired 100% to the actual 75%, 50%, 40%, 25%, that delta is going to increase. So that urge is going to increase. When you take an action, the action can fail, it can succeed. It can never be taken. You know, if you're sending a signal, and so these different results come back for a particular action, and we have schemes that represent these actions and their statuses. And the actions come from the device. That's covered in the Genesis video. So features are synthesized constituents of things in the external world. Percepts are received correlates of things extant in the external world. So the device sends us percepts, and from the percepts we have detectors which create features. And the features get associated with those percepts. Results are proprioceptive outcomes of attempted actions, and urges are interoceptive states of homeostatic variables. Images. We have different image schemas. George Lakoff was a big proponent of image schemas. And basically, these are arrangements, physical arrangements of objects. Above, across, apart, behind, beside, boundary, contact, container, path, together. We have simple relationships. Orientation and temporality. Orientation refers to whether the association is horizontal or vertical. According to Wickelgren, a horizontal association is one where complex ideas are represented by a strongly associated set of elementary ideas. So here we have genus, which is basically ISA in most knowledge representations. We have a mesa, which is below, and a meta, which is above. We have a grounding, which basically has a set of associated things that trigger a percept. We have a member, which says that this item is an example of a genus. We have a slot, which connects a category and an element. We have a swap, which is a substitution of an original item for a proxy item. We have a symbolism, which has a signifier and a signified. We have a tandem, which says that one item occurs before another. It's an ordering. We have vertical relationships. Vertical association is a complex idea represented by strong locally hierarchical associations and to and from constituent elementary ideas. So vertical association is a hierarchical, whereas horizontal association is not. So different, different says that these members are different. Incompatible means that these items are incompatible. Similar means these items are similar. Equal means these items are equal, and identical means these items are the same thing. We have gates. Gates are schemes that are synchronic or diachronic associations. Holland, Holyoake, Thagard, and Nisbet in their book in 1989 called Induction said that mental models are best understood as assemblages of synchronic, which means in unison, and diachronic, which means in series, rules organized into default hierarchies and clustered into categories. So these gates, we have categories, which is just a list of elements. A choice, which is a list of elements, but only one of those items is chosen. A league, which is a list of elements, but the majority of those elements will determine whether or not the league itself is activated. We have an ordering, which is an ordered list of items. A unison, which means that all the items have to be activated in unison, and a series means that the items are activated one at a time. And each one of these have a different merge type. And then we have structures. So everything else leads up to these structures being built. At the topmost, we have concepts. And concepts are comprised of classes and traits. Anything else is not a concept or is considered to be a pre-concept. So only concepts are concepts. All the other structures are pre-concepts. Then we have classes, and classes have genus. Oops, sorry. Classes have a genus, which is its supertype, kinds, which are the subtypes, categories, which are the properties that make up the class, traits, which are distinguishing elements of the class, distinguishing members of the categories, and members, which are examples of the class. So these are a little bit, fine to distinctions to be made. Finally, we have ideas, which are just a collection of slots, and prototypes, which are a collection of categories. So ideas are agglomerations of slots, prototypes are agglomeration of categories. Prototypes, the categories can be also considered roles. Classes are hierarchic arrangements of ideas in classes, and concepts, which sits at the top, are classes and traits reflecting aspects of reality. Ideas, just a list of slots. Pass this. We have prototypes. We have classes. The genus and kinds represent the position of the class. The categories and traits represent the idea, the characterization of the class, and the members are the examples. And then we have a concept. And a concept actually can start out to be empty. So we can have a concept that we don't know anything about, but the concept can be filled in over time. Concepts typically arise from reasoning and problem-solving activities. Concepts are often formed to represent inconsistencies or contradictions. As the inconsistencies are explained, the traits and classes are assimilated in a process called decentration. Therefore, it's typical for a concept to be constructed without traits nor classes. And then we have a lot of derivative structures. From tandem, we get hypothesis. So one thing coming before another, a prior thing coming before a later thing, can give us a hypothesis which has a premise and a surmise. And then we can have different kinds of hypotheses. We can have causal hypotheses, or in the physical realm, and we can have logical hypotheses, which says one thing implies something else. We can have members, and we can also have counterexamples or refuters. We can have a symbolism, and a symbolism just says that this particular signifier will evoke something that's signified. The signifier is present while the signified is absent. An example of that might be a boy or a child playing with a box and thinking that the box is a car. The signifier is the box, and the signified is the car. The sign is a symbolism that has a signifier that does not resemble the signified, and a symbol is a symbolism that has a signifier bearing some similarity to the signified. So an example of a sign would be the word cat, C-A-T, and the signified being an actual cat, the animal. So there's no resemblance between the letters C-A-T and the cat. And a symbol would be the box that the child was playing with and an actual car. In that sense, there is some similarity between the box and the car in terms of physical shape. Bearing from symbols, we have metaphors, which are direct correspondences between signifier and signified, and similes, which are indirect correspondences. From ideas, we can get events and an analogy. An event is a collection of slots, whereas an analogy is a collection of similes. From unison, which is an assembly, we can get entities, situations, statements, objectives, desideratum, states, so forth. From an objective, we can get an intention. An intention is an actor that has an objective. From series, we can get episodes, lessons, frames, actions, operations, and so forth. From categories, we can get problems, lacuna, themes, maxims, and so forth. And then from leagues, we can get theories. From concepts, we can get obstacles and contradictions. Anyway, I'm going to blaze through the rest of this. I don't know how much time we have left, maybe a half an hour or so.
An hour.
We have an hour? Okay, this is great.
You don't have to rush. I mean,
Okay.
Actually, the slower you go, the more I get.
Okay. Well, how is everybody else doing?
Well, yeah, we should get some feedback. Actually, can you guys hear me all right? Let's see if I can. Have you got your speaker on? But turn on your speaker, please. I'm not 100%. Got a little feedback here. Okay. Brett, how's it going, buddy? Can you say something? I'm not sure if we, I can see it coming through on text. I wasn't sure if we had the audio working or not, though. I don't know if you can you unmute? I see Bob Higgins.
I'm working on it.
Okay, if it's okay.
It looks like it's not coming through my speakers. Let me see if I can keep. So Brett,
Can you put up the chat?
Yeah.
yeah,
I hear you
okay,
loud
so
and clear.
we don't have any sound here. Let me see if
There's no
I
sound
can
where-
on my end.
No, there's sound coming through. It's okay. But can
Through
you
yours?
open up the chat?
Yeah, we've got it. We've got there. It comes with a chat.
And is everybody speaking in the chat?
I do see a message. I should be
Yeah,
able
you
to.
should monitor the messages.
I should be able to get my own output though. Okay.
So if you can turn off that, we'll resume.
Yeah. Okay.
Turn off your.
I got a quick question. Hello? Yeah, I just had a question on cross-parameter compatibility. So it looks like you're talking about a lot of different parameters here, but just wanted to see, like, when you're switching models. So, for example, going from Gemini to ChatGPT or GPT to Claude or some other model, like how compatible, or what can we use to make some of these parameters that you're talking about more compatible across platform or across AI models?
What is your parameter? What parameter are you talking about?
Well, like there's like Mirostat. There's different ones that are available on Olama. So they have like temperature parameters and different things like that.
So this has nothing to do with that.
Yeah, he might have been.
So yeah, I'm sorry. This has nothing to do with that at this point. But I'm going to continue. Are there any other questions? Okay, I'll talk about potentiation.
Yeah, well, why don't we go to the end of the?
Okay, we'll resume. Potentiation is associating based on activation. So potentiation is creating new circuits based on recent activation. To potentiate means to enhance or make something more effective or potent. Most accounts of potentiation focus on chemical changes in presynaptic and postsynaptic neurons. This focus is akin to describing how a spreadsheet program works by reporting on the assembly language instructions. From a high-level perspective, potentiation focuses on creating associations across varying brain regions, often via Hebbian learning, firing together, wiring together. For the present purposes, potentiation means creating associations, that is, schemes, using recent activation. So immediate potentiation, we talk about forming assemblies. So if we take in a percept from our observation mechanisms, and our feature detectives have created some features that are associated with the percept, we can activate all the features at the same time and create a unison assembly. And assembly is the word used and favored by Christos Papadimitriou, who's done a lot of work on assemblies in the brain. And so we can create a unison assembly, and that's basically it. Everything that's activated together, you create an assembly. Now you can ground those features in the percept. So with that unison assembly, we have a different mechanism which will create a grounding of that feature, so that whenever these features are activated, whenever all of these features are activated, it will activate the percept. Forming images. So image schemas, again, are arrangements. And when you have a feature that is next to another feature, we can say that this schema that says that this feature is beside this other feature. So those are immediate sensory potentiations, or immediate sensory circuits that can be built. For the short term, we can form entities. So entities are cross-modal assemblies. So when we have different unisons of features, we can create an entity from that. We can form tandems as well. So when two percepts are encountered one after the other, we can establish a tandem relationship. Similarly, if we encounter another percept after the first two, we can establish another tandem relationship, saying that this percept occurred and then this other percept occurred later. We can form series relationships. Once we know that things have occurred in tandem, we can say, well, these things actually form a series. And so it's useful to know that 3 things are linked together, or 5 things, are typically occurring together, not together, but one after the other in sequence, and so on. So it's useful to identify sequences of things, so we can form series. In the middle term, we can form vertical associations. So if we have different entities now, which are cross-modal associations, we can say that entities are similar because they share common features. So we can create similarity among entities. We can begin to form categories. We can say if 2 things are similar, then they may be in the same category. We have a categorizer mechanism that looks for similar things and creates categories. We can form attributes. We can say if there are categories that are activated and there are members of the elements of the categories that are activated, we can say that that category and that element form a slot, where the category is the property or attribute and the entity is the value. So we can start to form attributes of things. This is all using activation. We can begin to form ideas. Once we have slots, we can form ideas. Because basically we have attributes that are joined together. And ideas are just agglomerations of slots that are activated. Then we can ground ideas. So once we have an idea, we can associate that idea with a percept that was recently or concurrently activated. Now, so we have entities, we have ideas, and now we can say this idea was linked to this visual or kinesthetic or other percept that we perceived. Then we can begin to acquire language. This is long-term potentiation. Roland Hauser had a speaker-hearer model of communication. In the speaker-hearer model, the speaker has content, which is in some kind of type hierarchy, and the speaker can generate surface tokens. And these surface tokens come across as signs, what are called signs. And the hearer can recognize these signs, whether they're verbal words or visual signs, as in sign language, and take those signs in as tokens and convert those into types. When we adapt Roland Hauser's speaker-hearer model, we have what we call coordinations, which are the inferences in the totality. And from those inferences, we can generate observables, observables being speech, being sounds, being motions of our gesticulations. And those observables can be transmitted as signs to a hearer, and the hearer can receive those observables and make inferences based on those. And those observables can activate their coordination, their inferences. So language acquisition is about the hearer learning to recognize observables and creating the commensurate coordinations in their mental totality. So phonemes activated in tandem can be linked. So, we have the silence phoneme, and that can be linked as we receive percepts. We link them in tandem. And those percepts can represent different phonemic sounds. And those sounds can be perceived in tandem. And then choices are discovered for phonemes that have multiple transitions. So from silence, we have a couple possible ways to go. We can hear the sound or we can hear the sound k. And so that becomes a choice. Likewise, we can develop other choices for different transitions. And we can form a category for these percepts or the choices. So we can create categories. And then once we create categories, we can sequence these category activations. And then this series are equivalent to left associative morphemic transition rules or word rules, typically supported by long-range interneurons in the brain. So these series over time become transition rules for forming words. And we can construct ideas using this activation. So when we hear silence, then we hear the letter K, then we hear the letter A, then we hear the phoneme T. We can form slots based on those activations and then form an idea. That idea could be cat because of the phonemes that we heard. The process is reiterated at the next higher tier to create phrases by crafting left associative phrasal transition rules. So we have one idea. Ideas activated in tandem are linked. Again. And then the ideas can be grounded to the coincident percepts. Ideas activated in tandem are linked. We can substitute the actual morphemes or words for those ideas. So for example, the idea John, Julia is always working, dreaming. Then we can ground those ideas to coincident percepts. And then percepts are assembled into cross-modal entities. And ideas activated in tandems can be linked. And choices are discovered for morphemes that have multiple transitions, just as we did before. And categories are formed for the words and choices. And then we can sequence the category activation. So this series are equivalent to left associative phrasal transition rules, also supported by long-range interneurons. And then we can construct events using activation. So, if we encounter the word Julia is always working, we can create slots based on the category and the ideas associated based on their activation. And then we can create an event. In constructing events or phrases using activation. Julia is always working. We can locate scenes. So the locator adds scenes to the current venue and creates new venues and locales when the odometry indicates the robot has moved and current scenes no longer match known scenes. So this would make more sense if you watch the first video, where we talk about identifying scenes. Locating scenes activates known venues and locales when known scenes are activated. So we have scenes that are taken in by a robot, and the locator looks at venues that these scenes may be associated with. And it finds a venue and says, okay, these scenes I've seen before, and via associative memory, it associates those scenes with the venue. Then the venue is associated with the locale, and it sees some more scenes, and it finds the appropriate venue for those scenes. So as a robot takes snapshots of its environment, it can either retrieve or create venues for the scenes that it sees. There's a component called a mapper, a mechanism called a mapper, which links locales to venues. And then as it finds more scenes, it can create more venues and more locales. So what we have is individual scenes being linked to venues, venues being linked to locales. So the locator mechanism adds scenes to the current venue and creates new venues and locales when the odometry indicates the robot has moved and the current scenes no longer match known scenes. It activates known venues and locales when known scenes are activated. We can map locations. So the mapper creates, merges, or splits mental maps of the environment using landmarks and scenes. When a map is created, it has one region, one area, one place, one locale, and one venue. The current scenes are added within the venue. So it connects activated regions, areas, places, locales during potentiation. So we have a map. So the mapper creates maps. And when a map is constructed, it has defaults. It creates one region, one area, one place, one locale, one venue for the map. Any scenes that exist are tied to venues. Venues maintain a particular odometry within a particular trajectory threshold. A locale is an imagined or actual landmark. A place is a grouping of locales, an area is a grouping of places, a region is a grouping of areas, and a map is a grouping of regions. So we have this kind of structure. And the mapper, its job is to associate these locales and venues with places. So the mapper connects locales and venues based on the activation of the current map and the current locales and venues. So the mapper creates, merges, or splits mental maps of the environment using landmarks and scenes. When a map is created as one region, one area, one place, and the current scenes are added to the active venue. Connected, activated maps, regions, areas, places, and locales happen during potentiation. In extended potentiation, we form episodes. So forming episodes, basically you have events and the events are linked in tandem. We can form sequences of events, which are episodes. An event could be something like John has $40,000. Mary has a Tesla 3. Mary wants $40,000. John wants the Tesla 3. John gives Mary $40,000. Mary gives John a Tesla 3. John has a Tesla 3. Mary has $40,000. So these could be events, and all those events can be linked into an episode. And we see that events are simply groupings of slots. A slot is basically a category and an element of that category. And episode is basically just a grouping of events. We can form scenarios. So if we take the episode that we just had, prototyper can create a scenario, and then it can make prototypes out of these events. And the prototype is simply an event that has only categories. It doesn't have the elements of the categories. So it only has roles. So it can transform it can duplicate each of these events and just take the roles to make the scenario. And now it has a scenario. And what can you do with the scenarios? You can make frames. This is what George Lakoff was talking about. So you have a set of scenarios where a buyer has money, the seller has goods, the seller wants money, the buyer wants goods, then the buyer gives the seller money, the seller gives the buyer goods, the buyer has the goods, the seller has the money. You know, this is a scenario. And that scenario can be added to possible scenarios in a particular frame. The framer just adds a frame. It takes the relations and it takes the categories and it creates a frame. So each of these individual mechanisms has a specific job, and basically their job is to add schemes, assimilate or accommodate schemes. There are a couple more examples. I can probably skip those because we want to get to the interesting stuff. So forming instances, I'll just go through that. Forming classes. Forming hypotheses. Empirical causal hypotheses are that some situations follow others within a given time frame. Logical hypotheses that certain ideas are enabled in tandem may also be created. But forming hypotheses, forming theories, forming themes, and so forth. Forming lessons, forming maxims. Evocation, symbolisms, metaphors, and then the different associators that exist. Chunking, we'll pass through chunking, but chunking is basically ontology formation. And ontology formation happens in two phases, crunching and combining. Crunching, if we consider this as an ontology, where we have a category and elements. Here, the category is 55 and the elements are 1, 2, 3, 4. This is a random ontology. We crunch by finding similarities. And we, Like a compression? Yeah, compression. So you can see The genus means that 106, no, category 106 is a subcategory of 192. And so we can eliminate the redundancy. This is crunching. We're eliminating the redundancy. So we have 192. We have another genus, and we can remove the duplication. So we have the original, and we have the crunched. And then combining, we create new categories. So we can say any two items that share the same elements can be combined into another item. So you can remove those elements and put them in the new class. So 114, 104, and 107 have the same elements as well as 101, and so those items can be removed. And so we have an original ontology, we have the crunched ontology, we have the combined ontology. So we formed new classes. So this is category induction, basically. Chunking is category induction. And you have mechanisms for that. We have an intermission. We'll skip that. I'm making a video of this so you can review all of this in the video. Finally, the good part, solving. So solving is the process of retrieving or creating complex actions that bridge spatio-temporal gaps called problems between initial situations and desired situations, or that overcome causal contradictions. Causal contradictions are called obstacles, surprises, or failures. And it's a contradiction because you expect one thing, but you didn't get what you expected for whatever reason. In solving, the realm is causal or physical. The method is typically planning. Elements are observables and coordinations or events. Collections of these observables and events are called situations. The primitives we used in solving are actuations for robotics. The composites are actions, and groupings of actions are called skills. The gaps are called problems, the gap between the initial situation and the desired situation. Inconsistencies are called obstacles, and insufficiencies are called objectives or goals. Planning is the process of creating sequences of actions or actuations, and specialized problem solvers propose viable action and actuation paths from situations to objectives if there are no relevant existing paths. A problem solver would propose a path in the form of a complex action. Observables received by a perceiver are forwarded as situations to an action selector and concurrently to the problem solvers. We have events, situations, episodes. And actuations are primitive motor behaviors that a device can perform. Like a robot, you would say, ask it to close its left hand. And actions marshal an ensemble of actuations to execute a complex behavior. Actions are physical and exert forces upon objects. Actions may be cross-modal. Cross-modal means you might see, hear, and feel something at the same time. An action can have different actuations or sub-actions. Skills are collections of actions. Problems are spatial temporal gaps between initial situations and desired situations. And obstacles are causal contradictions that expose differences between expected and unforeseen situations. Objectives or goals are conditions or events that are desired and that are expected to resolve a deficiency, fill a gap, or correct a situation once achieved. And this is a topic map that kind of shows how these things are related. Problem, skills, objectives, obstacles, actions, actuations, and so forth. And this occurs in the causal realm. So in solving, what is the game? The game is that you start with a particular situation, which is, a set of reifiers can represent your situation, a set of schemes. These are active right now. You have an objective. The distance between the initial situation and the desired objective is called the problem. You can choose a set of actions to resolve that problem. And you may encounter obstacles along the way that have to be resolved because the actions are insufficient, or you don't have enough information, or you have to learn new things about the environment. So that's the solving game. What mechanisms can you use for solving? There's a whole bunch of different mechanisms. These have nice names. But basically, you can use analogical, associative, hierarchical, means ends, plan space, state space, graph, lesson-based, episodic, or genetic methods to solve problems, to bridge those gaps. Analogical planning, associative or case-based planning. Now they use neural nets for associative planning. That's fine. Hierarchical planning, means ends planning, plan space planning, state space planning, graph plan planning, lesson-based planning, episodic-based planning, genetic planning. Reacting basically is you have a device, you have a perceiver, and you have a bunch of actions that can be taken, and the reactor picks a reliable action based on what it perceives. Deliberating is a little bit different. Deliberating is when you have a perceived situation, you have a bunch of actions available to you, but you have objectives to fulfill. So you want to find an action that is applicable to the current situation, but also fulfills your objectives. Whereas in reacting, you want to find reliable actions. In deliberating, you want to find useful actions. You just don't want to take an action that doesn't achieve your objectives. You want to take an action that that will get you closer to your objectives. So that's the difference between deliberation and reacting. Okay, this is the last section, or close to the last section. Reasoning is what enables the human mind to go beyond mere perception, habit, and instinct. Reasoning is a process of retrieving or creating operations that use knowledge transmutations to both bridge logical gaps called lacunas, and between initial premises and desired conclusions to resolve contradictions, explain phenomena, justify conclusions, and persuade oneself or others. Planning with actions in the causal space is like planning with operations or knowledge transmutation in the logical space. In the causal space, problem solvers use actions to find pathways among situations to achieve objectives. In the logical space, reasoners create and use operations to bridge gaps in understanding and form logical inferences. Lacuna are akin to problems. Lacuna are gaps in understanding that arise from logical contradictions or failed reasoning. Lacuna can be bridged by operations. Operations are created by reasoners that specialize knowledge transmutations to fit a particular context. Together, operations and theories form non-monotonic metamodel. Okay. So whereas with solving, you had particular vocabulary, with reasoning, you have different but similar vocabulary. In reasoning, the realm is logical. The method you use in planning is solving is planning, but the method you use in reasoning is inference. The elements are propositions as opposed to observables or coordinations. And the collections are called statements. The primitives are logical transmutations or knowledge transmutations. The composites are called operations as opposed to actions. And the groupings are called knowledge. The gaps are called lacunas as opposed to problems. And the inconsistencies are called contradictions as opposed to obstacles. And the indeficiencies are called desiderata as opposed to objectives. So basically, inference is the process of deriving new knowledge. Learning is inferencing plus memorizing. You have propositions, ideas, and events. You have statements, which are basically just unisons. And you have theories, which are leagues or agglomerations of operations, ideas, everything. We have transmutations, which are primitive knowledge manipulation functions that can be applied to premises and to known background knowledge to produce new inferences. So for example, we have a deductive referent generalization, which takes a premise and a list of known background knowledge. And for each premise in the premises, it picks a referent from that premise and searches for a genus relationship where the reifier is known, the mesa is the referent, and the meta is bound to a new symbol. And it copies that reifier into a new scheme and substitutes the reference for the meta. This is referent generalization. There's a host of reasoning transmutations that can be done according to different strategies. So you have generalization, specialization, abstraction, concretion, and so forth. And you have different ways of doing that. You have deductive, analogical, inductive, transductive, infralogical, Piagetian, and alternative strategies for accomplishing these things. Operations combine transmutation and other operations to create inferences. An operation posits that if the premises are activated and the assumed background knowledge exists, then results can be obtained and activated by performing the subsequence of sub-operations. The premises and known background knowledge produce the results. Operations are composable and support reversibility. Knowledge we can define here as collections of operations, just as skills were collections of actions. Lacunas are gaps in argumentation between initial premises and desired conclusions, and contradictions are logical inconsistencies that expose overlaps between complementary category. So for example, we have a category P and a category not P. If we have something that participates in both, that's a contradiction. Desiderata are essential propositions that are not yet proven. And reasoning can be formulated in a topic map very similar, if not identical to solving. So the game, what is the game here? The game with reasoning is that you start out with premises, you have some desiderata things that you want to achieve, you have a gap between the premises and the desiderata, which is called a lacuna or a problem. You have operations that you can use to solve, to close that distance. And you may encounter contradictions along the way that have to be resolved. So we're just about done, but we have preconcepts, which is everything that is not a concept. And preconcepts, using reasoning with preconcepts can lead to a bunch of errors. Artificialism among them, the belief that everything has a creator, whether an object or a person. Animism, the belief that everything is alive, especially inanimate things. Magic phenomenism, which is a confusion of correlation and causality, as well as erroneous ascription of causes. So these can arise by preconceptual reasoning. And you have intuitive inference as well. Intuition is the linking of preconcepts to operations. Intuition is semi-reversible, eventually leading to reversible subsystems. Transductive inference is reasoning from ideas to ideas or events to events using preconcepts. It differs from analogical reasoning only in that analogical reasoning employs concepts. And infralogical inference is reasoning which establishes that objects are encountered at different moments in time, however different in appearance, are the same. So infralogical reasoning establishes that the picture hanging on the wall 5 seconds ago is still the same picture you are viewing now. Errors in infological reason may lead you to believe that the cat you spotted on your morning walk 5 minutes ago is the same cat you are now encountering. Egocentric phase children often make these errors. Piagetian inference, he identified a bunch of reasoning methods, sensory motor, intuitive, concrete, and formal. Concepts. Conceptual inference occurs during a person's operational development period. And basically, we have different conceptual inference strategies. We have deductive inference. Given premises and background knowledge, we can derive conclusions. Inductive inference, given conclusions and background knowledge, we can hypothesize premises. And analogical inference, given premises and background knowledge, we can hypothesize similarities and thereby derive conclusions. And we have alternative inference strategies. A lot of different transmutations. So among the transmutations, we have, for example, generalization and specialization. We can do deductive generalization and specialization. The purpose of generalization and specialization is to substitute a generalized or specialized value for one in an existing premise proposition. Given a situation in a genus hierarchy, a new situation may be accommodated by substituting the more general or special element of the background hierarchy. So we say there's a situation, Chucky has a pit bull, and that's our premise. And we know in our background knowledge that pit bulls are dogs. So pit bulls have a genus of dog. We can therefore derive that Chucky has a dog. That's generalization. Specialization is the opposite. We can say that Chucky has a dog, and we know that terriers are dogs. Therefore, we can say Chucky has a terrier. That's a specialization of the initial situation. We can talk about abstraction and concretion. The purpose of abstraction or concretion is to reduce or increase propositional information. Abstraction removes elements from a situation while concretion adds elements to the situation. For arguments or reference participating in an abstraction hierarchy, abstraction concretion substitutes a higher or lower element in the hierarchy with the argument or referent. So we can say a situation, the quick fox, and to abstract it, we remove information. So we can say the fox instead of the quick fox. Likewise, for concretion, we can start with a situation that says the lantern, and we can remove information. We could say we can add information. We can say the green lantern. So we've concreted the premises. And then lastly, we'll talk about assimilation and dissimilation. The purpose of assimilation or dissimilation is to construct a new proposition, argument, or referent based on its similarity with an existing one. So we say a cat has feet. We can say the cat has a similar motion to fog. And you can thereby say the fog has feet. This is poetic, of course. You can say dissimilation. You can say wood floats. The wood has a different density than stone. And then you can say stone doesn't float. So that's dissimilation. And then, agglomeration, decomposition, and so forth. Agglomeration creates new categories by clustering existing categories into larger groupings, and decomposition creates new categories by dividing existing categories into smaller groupings. So you can say if you have a category wallet, money, keys, and a category notebook, then you can agglomerate these and say wallet, money, keys, notebook. Decomposition would be saying you have a category wallet, money, keys, notebook, and then you can split those or decompose those into separate categories. And I think that's about it. I'm going to fast forward to the end to take questions. There's a lot of things, but we'll pass up those for today. The book, Coding Artificial Minds, will go into the weeds about building these systems. And the book, Building Minds with Patterns, is available on Amazon. That talks about building minds with design patterns. And that's about it. Thank you.
All right. Cut your
Mic?
mic and
Yeah.
speaker.
Okay.
I think, all right.
And
Well,
I'll stop sharing.
can you guys hear me okay? Let's see if I got,
Yeah, I can hear you.
okay. Hey, Bob. Yeah, yeah. Okay. Well, that was great. I mean, it's been a while since I've, in this age of, here's your transformer and here's your data and here's your AI. It's nice to see a full brain structure kind of outlined in such detail. So thanks, Mike. That was quite a, I think one thing that, I think is important about your structure is that the schema is uniform throughout.
Yeah.
So and I think that might get lost because we're looking at all these various different basically categories of reality, but you use that common denominator of the single schema. And a couple of things I thought were really interesting was the dreamer. You have the different kind of variations of reality, possible realities, and one question I had was the registry. That's a different data structure, though.
Yeah, the registry is just something for the overall system.
Yeah.
Are there people that?
Yeah, we can entertain other questions. Sure.
Anyone have any questions?
I have a question.
Go ahead.
Have you actually built any of this in software?
Yeah, actually, the programming language, the underlying language, we have different iterations of. And what we're attempting to do is to get a robot connected to such a system. So we're putting together the hardware, software, and it's been in process for a while, but we're trying to get this actually implemented, have a prototype, and then scale up. We have an educational robot that we're using, and then we'd like to scale it up to Tesla or Figure One robot or one of these industrial robots, and probably run it on hopefully a supercomputer, maybe the Colossus or
Frontier.
maybe the Frontier. We'll see.
Well, one of my big questions has to do with your language model. Have you built that? That doesn't require a robot.
What are you talking about, the language model? What do you mean? The ontology?
Well, you talked about how a language model was built so that you could recognize phonemes and blah, blah, blah on up to recognizing a sentence.
Yes. So all of that is in process. Yes.
Okay.
You could use, I mean, that's pretty much been conquered already by, neural networks. So it seems like you could just use some existing.
So the difference between this and the neural network approaches, most neural networks, not all, they have continuous neural networks, right? So the neural networks, generally, they are frozen at a particular point in time, whereas this is a continual learning model, so that any new, for example, in the case of language acquisition, any new utterances that you make are taken in, and over time, some utterances, if they're not used, can be forgotten, whereas the core utterances will be retained and can be used for both generation and recognition. So this is a online continuous learning methodology.
Okay, so given the language, you hear an utterance of something. How do you know what that refers to?
So as you saw in the utterance, there's a grounding process that's also occurring during potentiation. Right? The grounding is a relationship between a set of associated things and a percept. And so we have cross-modal or multimodal grounding in time. So
if you've never heard the sound, the utterance before, how do you ground it?
you ground it to whatever is occurring at the same time.
That doesn't make any sense, because what may be occurring may not have anything to do with an utterance that you make.
That's correct, but that's okay, because those things may fall out over time. And actually they do, because, for example, I'm saying to you the word visible, which is a nonsense word, but you've just now taken in that word visible. And in 20 years, when we meet again and I say visible, you will remember that it was done over the internet at this particular point in time. And the actual referent of visible, it doesn't have any referent, but the fact that you heard it at this particular point in time may evoke the memory of us talking about it right now. So we take in a word in a particular context. The word may have a referent, but there may be initially, if you think back to when you're a child, you may not have known the reference to the word. Do you?
Well, okay.
Do you understand what I
Part of
said?
the-
You don't have to agree, but do you understand?
Part of the language problem is not just recognizing words and putting them together in sentences and recognizing a sentence, but understanding what it's telling you to do. So if I'm giving a robot a command, I take that sentence, those words. How do I know what I'm supposed to do?
Initially, you don't. But over time, you will learn what you're supposed to do.
How?
It's everything.
I think you have a connection in your totality structure to action. So eventually you would connect the language through some chain of network to an action. How
Yeah,
exactly? I don't
But
know.
so
How do I
everybody,
do that?
everybody's looking for shortcuts, right? And you can shortcut and short circuit the system. But what I'm talking about is a system that learns autonomously on its own through its own experience. Does that make sense?
Yeah, but I still don't see how you do that.
What do you mean by you don't see how you do that?
I give you a word that says go forward.
Uh-huh.
You've never heard those words.
It has no idea.
Wait a minute. You've never heard those words before. How do I figure out what that means?
Yeah, basically it's a learning.
It's a learning process.
Yeah.
It's just like taking you back to when you're in a baby or in elementary school. You'll have to learn those meanings of the word over time through experience, through embodied experience.
Okay, but what I'm saying is I don't see in your architecture any way to do anything other than just learn that those words were spoken. It doesn't tell me how they get used or how you learn what they mean.
I understand. And that's fine. You don't have to see it, but take a look. I would recommend that you watch the Genesis video that's on YouTube under the Cognitive Architectures channel. And that might give some clue as far as the observation is concerned. And then the last video in the series, I'm going to put up a video hopefully tonight on this talk I just gave. And then the last video in the series is on development, which is the final section, section 4 of this talk. And that video is about learning from infancy through adolescence. So maybe the answer might lie in that.
Maybe we should see if there's any other questions.
Thank you, Bob. I appreciate you.
Yeah, thanks, Bob.
I appreciate you.
Good, great question.
Yeah.
I've got a huge number of questions, probably more than we have time for.
Okay, but is anybody else, Brett?
Brett is asking for the URL.
Yeah, for the,
Let me see if I can put that in the chat.
I've question. I mean, at one point you said you made a reference to feeling good or bad, and I was wondering how fine-grained your emotional typing is. Like feeling sort of good, feeling. Right, I know. Okay, you've got different things like arousal and things of that nature. So. I mean, can you comment on that? Like, how do you design for the good and bad?
Right. So the emotions are very coarse grained, they're not
Coarse-grained.
fine grained. And we only deal with 2 dimensions, which is arousal and valence. And those dimensions are done on a scale from -1 to +1. So, you know, you can get at most, it's excited and it's good, feeling good, or it's, you know, feeling bad and it's apathetic. So
Yeah,
that's about the range of the emotion.
it seems like, you know, human,
But
yeah, it does come down to ultimately it's good or bad. It seems like it always comes down.
yeah, but there are other people with other systems out there that really delve into emotion, and they have maybe
Right.
12 emotional parameters as opposed to just 2.
Yeah, that's kind of what I wanted to see. if
And
that
so there
comparison,
are many systems out there that have you know delved into that more.
Okay, any other questions? I don't think we're gonna get kicked out of here immediately. So I think we can entertain some more discussion. Anybody, we didn't have anybody show up in person, but any more questions? Bob, it sounds like you had a whole slew of them.
Yeah, if no one
Yeah.
has any questions, then go ahead, ask them more.
Okay, in your memory, you have one huge memory. Do you divide it up into things like semantic memory, working memory, episodic memory, procedural memory?
No.
So
But you can
to
see all
find
the-
anything is going to be a
Hang on,
huge,
hang on. You could see all of those elements in there.
You
but to
could,
find any one of those elements is going to be a huge search problem. And it's going to take an enormous amount of time.
Potentially, but there are many methods for making that easy. So, for example, in the first video, I talk about associative memories and associative retrievals.
Yeah, which we really don't know how to do yet.
No, we know how to do associative memory very well. Actually, that's what ChatGPT and all these other neural net-based systems are. They are associative memories.
No, they're not.
They are.
No, they're not.
We can agree to disagree about that.
Okay, we disagree about that one. I've built a number of neural networks. Thank you.
Nobody's questioning that. But I'm just saying, what is the definition of associative memory? It's a memory that links features of an entity to the entity. Right?
No, it works backwards.
I'm sorry?
It works backwards, and associative memory works backwards.
Okay, so we can argue about the definition of associative memory as well. But, you know, that's
Okay, one more question that really bothers me.
go ahead.
How do objectives get set? You talked about objectives. How do they get set?
So there are different regions in the initial diagram. I showed that the artificial mind has different components. It has observable components. It has coordination components, which is what we talked about today. It has reflection components, and it has consolidation components. So when the device initially connects to the artificial mind, it registers itself. So the device has on its special software called a psyche, and the psyche registers itself with a component in the mind, a mechanism in the mind called the registrar. And the device sends to the registrar a bill of lading. It says, this is my name, this is my URL where I can be contacted. It says, these are my needs. And a need is a homeostatic variable. For a robot, the needs would be energy and Wi-Fi signal strength. So it says, these are the needs that I have. And then it also says, these are the actuations I can perform. And it sends a long list of actuations.
The needs, the objective. pretty much.
So
So
the
that's-
needs are sent, after that registration happens, the needs are continually sent to the mind from the psyche to the perceiver agent. And the needs reflect the urges or the urgency of each of the homeostatic variables. So for example, energy is at 100% when you start out, but then it dwindles down to 70%, 60%, 50%. The urge is the delta between the desired amount and the actual amount. The desired amount for energy is 100. The actual amount may be 50. The urge is that delta. It's 50. And the urge increases over time. So this urge that increases is monitored by a mechanism that says, oh, this urge is increasing. Let me set a objective or create an objective to reduce that urge. And so the attenter is the monitoring agent that will create an objective to reduce the urge. So that's how the objectives
Yeah,
are created.
they're just input by the device, basically.
Yes.
Yeah.
Does that make
Oh.
sense, Bob?
No, it doesn't, because all that says is he has an urge to keep alive.
I'm sorry?
All that says is the robot has an urge to keep alive.
That's right.
Well, that, yeah.
So
That's his only objective.
No. Then there are other, in addition to that, there are other mechanisms.
What are they?
So I'm about to tell you. In the reflection agent, among the reflection agents are other objectives. Other mechanisms. One mechanism is called the explorer. And what the explorer does is it looks for actions that have been created. And if the action doesn't have any results, it says, what is this action going to do? And then it creates an objective to perform that action. And then once the action is performed, it copies whatever happened as a result and adds that to the action. So it's a form of curiosity. It's going to try different things to see what's happened. This is what teenagers do. This is what little kids do. They say, what happens if I try this? Or what happens if I do that? And so that's another way of setting objectives. Finally, there is a mechanism for imitation and play. For imitation, what happens is you observe, you have some observables that you've seen, and the goal, the imitator tries to reproduce those observables. And so how does it reproduce those observables? So it might have heard a sound, ba, or something like that. And it says, what happens if I try to reproduce that? Let me see which actions or action combinations will reproduce that sound. So the imitator is also a component that can set objectives. And lastly, you have a play. In play, you create what are called ludic goals. Goals that don't have anything to do with survival, goals that are just about trying things out. So a ludic goal might be to build a tower of blocks or something like that. So there's a component also in the reflection agents that is about play. So there are many ways to generate goals in the system.
Thanks, man.
Does that answer your question, Bob?
Not very well, thank you.
I Like, we have time for maybe one or two more. I have one additional question, but
Go ahead. Somebody else, a couple.
yeah, if we've got any other questions.
Yeah, there's a bunch. Is there
There are
a
a bunch?
mechanism to convert continuous sensory non-symbolic
Oh.
numeric values into
I
symbolic
didn't see
representation?
I didn't see that.
Brett, could you elaborate on that question?
Yes, I put an example there in the chat as well. For instance, you have a microphone. It's continuously measuring the volume of the different pitches. If you've ever seen a spectrogram, you know what a spectrogram looks like. Shows the dark area where there's a volume for a certain pitch.
Yes.
And do you have any mechanism that will convert continuous sensory non-symbolic, as in numeric values, into symbolic representations?
Yes. So what we do is we take samples of the data. So there's a good video you should watch, which is called Genesis. It's on that channel. It was a video I put up most recently. And we talk about perception or observation. But the short answer to your question is, we take in the data, the numeric data, as a string, as a message. And we take that message and we convert that message into a scheme or a reifier, right? That message that you send in is a percept. And there's a rate at which you're sending the message. For video, it's 30 frames per second. You can ease up and do like 10 frames per second or fewer. For the audio, you take in that information, whatever the information is, and you hash that information into a unique ID, a unique reifier number. So now that information is represented as the reifier. So that's already the symbolic transition. You've taken one or a group of numbers or an object, and you've converted that object into an internal representation of that sample. And now that unique identifier, that unique reifier, is used going forward. Does that make sense?
Yep, that sounds great, Michael. Thank you very much.
Oh, you're welcome, Brett. Oh, but watch that video. That video will show exactly the process. We talk about
This
that.
the video is on the URL there, Cognitive Architectures, is it?
Yes, it should be. If you click that URL, just see if you can, if I typed it in properly, you can get there, and then you should see the video that's called Genesis.
Okay, I'll find it. Thank you.
Asher, you had a question?
Yeah, sure. Just wanted to kind of get your idea on self-modifying systems. It seems like what you're trying to do here, eventually you're going to have to start modifying some of the own aspects. So what's your thoughts on that?
Yeah, so there are a number of videos there on self-modification. So we talked about in the initial diagram, you have the observation mechanisms which take in information from the device. We talked today about the mechanisms that make new inferences, the coordination mechanisms. And then there are the reflection mechanisms. And the reflection mechanisms are all about self-modification. So the reflection mechanisms, basically, I talked about one reflection process already, but then you have other reflection processes. You have behavior modification. So we have a set of actions which we talked about earlier. These actions are constructed by the solvers. But the question happens is, what happens when you take an action and it doesn't work? The solvers predicted a certain result, and then that didn't happen. Okay, so now you have you attempted an action, and the action performed, but it didn't achieve the results that were expected. So that action actually failed. And now there's a tracking mechanism for the attempt, that the attempt did not achieve the results expected by a certain time frame. And so now there is a whole regulation pattern where there's something that tracks, a correlator that tracks the results of each action. And then the correlator goes to a regulator and says, hey, this action didn't achieve the results. The regulator can modify the action based on either priority modification or genetic modification. Priority modification is just saying that raising or lowering the priority. So raising the priority would be reinforcing the action, and lowering the priority would be correcting the action. And just say that this action is to be more preferred or less preferred in future when attempting this goal. And then genetic modification would be doing things like crossover. If the action was beneficial and successful, we want to combine this action with other actions that are also beneficial or successful. But if not, if the action was failing, then we just like to leave it and let it die out. It's kind of like Darwinism.
You've got an evolutionary mechanism.
Right,
Yes.
exactly. So, for example, if you like eating ice cream and watching movies, you might want to do them both at the same time. Hey, let's watch a movie and eat ice cream. You know, might get double the fun. So, it's kind of like that. Does that make sense?
Yeah, a little bit. I just didn't quite get on the first example. You were saying how things kind of like, if it doesn't work out, you would maybe modify different parameters or variables to try to get it to work better. But I didn't quite understand what you're trying to do with that.
So there's a video called Regulation. Can you go to the website and see if you see that video?
I didn't see the video, but I looked at your YouTube site really quickly. Yeah.
So on that YouTube site, there's a video called Regulation, which is specifically about that. There's also a video called Motivation. I think there should be a video called Motivation on there. That's also about the motivation pattern. And so those would give good indications of the behavioral modification that you're talking about. And also, there's a book called Building Minds and Patterns. I don't want to plug my own book, but you can take a look at that one. That's available. Asher had a lot of designs seem to be basically a tree structure and classifying various aspects of the knowledge tree or word tree. So, ontology. I call it ontology. So there's an ontology, a multi-type ontology, and that's what the knowledge representation is.
You count your ontology as first principles, basically. Seems like. If there aren't any more questions, we went through the written in questions. We're pretty much over time. I have one final question. That's okay. So, how would you say, in the big scheme of things, your cognitive architecture compares to some of the other cognitive architectures out there? What benefits in particular does yours have? And I know, knowing you for such a long time, you're really inspired by Jean Piaget. Why? Why was that? And so it's kind of hopefully the climax of the event. What led you to Jean Piaget, and how is that going to get you a cognitive architecture that's superior to the other one?
So I don't know about superior, but I do know. So I stumbled into Jean Piaget accidentally. I picked up a book working at Columbia University when I was a teenager in their computer science department, and I saw a guy hawking books on the sidewalk outside of the university, and I said, "Hey, that looks interesting." It says Jean Piaget, The Development of Thought. I said, wow, it's a nice nifty title. I'd forgotten how much I paid for it, maybe $5, maybe $10, I forget, maybe $15. I don't remember.
It was good investment.
Yeah, and then I read the first paragraph of that book when I was about 16, 17 years old, and no, 16 years old. And I put it down because I did not understand one word of it. And then it took me maybe 30 years to get through it, cover to cover. And I actually also bought the second version of it. And it got me to thinking about how to build a system like people. And I read a bunch of his other books, Play, Dreams, and Imitation in Childhood, the Classification and Seriation, and quite a few others. And then, so it got me thinking about how in his mind, he interviewed a lot of the children and had, his own quirky method, but how in his mind, the pieces fit together. So basically, this is just putting the pieces together. Does that make sense?
Oh, yeah. How do you think it compares to other cognitive architectures out there?
So a lot of other architectures are engineered, and a lot of people just want to do engineering as opposed to saying, this is how we believe people operate. There are a few that say this is how we believe people operate. So SOAR, ACTAR, and a few other cognitive architectures start from how do people work.
Yeah.
And then, they build their systems based on that. And then they have to engineer the system.
It seems like yours is drilled down pretty far and, pretty good detail in terms of, mental operations.
Yeah. So that's what I'm hoping. So, we'll have the proof of concept, and then once that's there, then, we'll see.
All right. Well, I guess we can wrap it up. Thanks.
Any other-
Looks like Bob.
Any other questions? Any final questions?
Yeah. Thanks everybody for participating, and thanks to Michael again.
Thank you.
Yeah, it was refreshing, like I said before, to see, here, this is not your transformer data and that. It's okay. So I guess we'll wrap it up. Thanks, Asher. Thanks, Brett, and we'll see you next time, guys.
Thank you. Email, hang on, one last thing I'll put in the
Okay.
chat. Email subthought@hotmail.com for questions. Send that.
Okay. Yeah, and we can, if you have any other questions, there's the event web page on Meetup. Okay. See you guys later.
Thank you.
Oh, whoops. I have to stop the recording. Like, a pretty big recording.
Yeah, I'm sure it is.
Um,
Okay, cool. Well, that was hopefully informative.